Hello everyone, this is Sam from class and I'm back here to talk about what happens when we make our Zimmermann-Draxler transition state have stereo centers already existing in some element of it. So I have here the example that we just looked at. So when I have this ketone right here, I've got a bulky group, I form the enolate, and it's going to be a cis type enolate because of that bulky group. And I'm reacting this with this aldehyde here, and we saw in this reaction that because it's a Z enolate, we're going to get the syn-aldol product, and this was my Zimmermann-Draxler transition state right here. And then when we unravel that to the product and then translate that into a more standard drawing, we got this syn-aldol product. But I want to remind you that we're getting the racemic product here. And that's because there's really nothing in this transition state that would cause the enantiomeric transition state to be at a different energy. What does that mean? Let's take a look. So I'm going to go here. I've already drawn these. So here is the original transition state that we just looked at. Okay? This has an enantiomeric transition state right over here. All it is the enantiomer. It's a mirror image. And there's nothing about these two that would lead them to have different energies. And so while this one would lead to this product, where I got both of these groups on wedges, the other Zimmermann-Draxler transition state is going to give me the product where they are both on hashes. And again, the reason for this is that there's really nothing to bias these two transition states to say, hey, this one's going to be higher in energy than this one, which would mean this would be the favored one, which means this would be the only product I would get. There's nothing here that's doing that. These are at the same energies. Same energies, because they're enantiomers of each other. Okay? And what that means is each is equally favored, meaning I'm going to get a mixture of both of these products. 50% of this one and 50% of this one, aka it's racemic. I'm getting a racemic mixture. So if there's something that I could do to these two transition states right here that would lead them to be different, then we might have a way of favoring one over the other. And that's exactly what we're going to talk about here. And this is called an Evans-Aldol reaction. Okay? And the reason we call these Evans-Aldols is because they use the Evans auxiliary that we've already seen in class. So let's take a look at these Evans-Aldols. Okay? So for Evans-Aldols reactions, we use the chiral oxazolidinone auxiliaries. Okay, we've already seen these for asymmetric alkylation reactions. We're going to see how these affect aldol reactions. So to show you how this works, we're just going to dive into an example. So let's say we are going to have this Evans auxiliary here. I'm going to use the benzyl one. And I'm going to use the S-configured auxiliary, and that's because I'm going in this direction here, so this is S-configured. And I'm going to have it attached to this ethyl substrate right here. Now, when we form enolates from the Evans substrates, I'm going to use the dibutyl boron Lewis acid. In this case, we use Hunig's base in methylene chloride. And in this particular instance, we're going to get the cis-type enolate. So the methyl group is going to be on this side, and that's because it wants to be away from this big, bulky auxiliary that's got this big, bulky phenyl or benzyl stereocenter coming out of it. So my boron is going to be held in between both of those carbonyls. It's called a chelate when it's being held like this by two positions on the substrate. It's like a little claw that's going to hold on to that boron. And again, we're getting the Z and or cis type enolate here. Now, it turns out that this is actually not the reactive form of this enolate. It's going to be in equilibrium with the form where the boron has disattached from this oxygen right here. So let's draw what that looks like. So that's going to look something like this. And again, this is the reactive form. And so what that means is that this bond right here has free rotation. And we're going to see that come into play in the Zimmermann-Traxler transition state that we're going to form. So once we form this enolate, let's suppose I'm going to add some isobutyroaldehyde. That's just a fancy way of saying it's this isopropyl aldehyde. That's going to be my quench here. I want to know what type of product am I going to get. Now, of course, we already know that it's going to be a syn-enolate product because it's or a syn-aldol product because it's a cis-type enolate. So really, my choices here are going to be the following products. I can either get the syn product where they're both on wedges like this. And again, I'm going to try and do these aldehydes in blue, just so we can follow it through these reactions, see it in the transition states. Or I might get the other product where they're both going to be on hashes. And the Zimmermann-Traxler transition state for these is going to tell us exactly which of these two products we can expect. Oh! That's what happens when you try and hold two pens in the same hand. See? Not easy. Alright. So I need to figure out which of these two products I'm going to get, and that's again where the Zimmermann-Traxler transition state comes in. So I'm going to get a new sheet here so I can get rid of my mark, and let's see what this looks like. So I'm going to draw these in the same way that I always do, and that really helps me solve these problems. I really recommend you always draw your enolates and your Zimmermann-Traxlers in the same relative orientations. Okay, so here's the double bond of the enolate, and I'm going to draw in my aldehyde. And again, as per usual, I'm going to put the small group in that pseudo-axial position, and my bulky group will be in the pseudo-equatorial position. That's going to be bound to the boron of the Lewis acid. And we're going to get something like this. And now you can see why this is the reactive form. I need the boron to have one free binding site on. I need that vacant p orbital to be open. If it's chelated like this, I can't bind another group to the boron. And if I want to bind another group to get to my Zimmermann-Traxler, it needs to be free like that. So that's why that's the reactive form. Now I can go ahead and fill in my methyl group here and my H there. And now the key part comes in. Before, in the substituent that I was drawing in this position, it was a phenyl group, actually, in both of the examples we looked at last time. But now it's a group that has a stereocenter on it. Here's how this works, and this is really the key. My auxiliary, because it has free rotation, is going to orient itself like this. The dipole on this carbonyl wants to be pointing in the opposite direction of the dipole on the aldehyde. We want these dipoles to cancel out. And that's just an empirical observation that's been made over many years of studying this reaction. Now if we do this, my benzyl group will be on a hash. And that's actually why the blue aldehyde approaches from, we can kind of see it as the front face here. If this is my chiral auxiliary, the aldehyde wants to come in from the front, because the chiral auxiliary has the big bulky benzyl group pointing away. So the aldehyde wants to come to the side, pointing away from the bulky benzyl group. Okay? Now I know I've done this right because I've maintained my S configuration at that stereocenter. So I know I've drawn this properly. Let's take a look at the other transition state where the aldehyde is coming in on the wrong side. Let's see what that looks like. And actually what this transition state's somewhat going to look like is, it's almost going to look like an enantiomer. Okay? It won't quite be the enantiomer, but it'll be close. So I've got my boron, and that's going to be bound to both of those oxygens. So here's my aldehyde. H goes in the pseudoaxial, bulky group in the pseudoequatorial. Okay, and then there is the enolate. I'm going to fill in my methyl and my H. And then I'm going to put in my auxiliary. Now again, I want to orient in a way where the double bond of the auxiliary is pointing away to cancel out electronically with the double bond of the aldehyde. Now if I do this and if I maintain my S configuration, that means this group is on a wedge. And that is bad news. The aldehyde is coming in on the same face where this big bulky group is pointing. If we want to think of it this way, the 1,3 diaxial interaction is going to be really, really bad between the phenyl and the N-butyl, and then the phenyl and the hydrogen there. That's going to be really, really sterically hindered. And another way we can think of it is this bulky benzyl group is pointing way out into the middle of the ring. So it's extremely sterically hindered, and this would be very much disfavored, mainly based on steric grounds. Okay? Because the aldehyde is simply approaching the wrong face. This is the favored intermediate. Or rather the favored transition state. So let's unravel each though, just for practice, to see what our products are going to look like. So I'm going to go ahead and convert this over. So the aldehyde becomes the hydroxyl. I've got my H here. I've got my isopropyl here. Go ahead and fill in my methyl and my hydrogen, my chiral auxiliary. And now my carbonyl is in the back there. And if we unravel this, the product we're going to get, and remember, this is the favored product, this is the one we actually form, I won't walk you through this because we already saw that in the last video, but for practice you can practice doing your RNS configurations to see how I got this product. But this is going to be the product that forms. If we unravel the other one, we're going to see we're going to get the other product. So let's go ahead and do that really quick. So I'm going to draw the aldehyde first. Okay. And then this is going to come down. Got my methyl and my H. Okay, I'm going to get that structure right there. And if we convert this over, which again I recommend you do for practice, but what you're going to find out is that they're both going to be on wedges. But because this one's ultimately derived from the disfavored transition state, we don't expect that product to form. This is going to be the only one that we form. Okay? And that's really how these work. So when you're drawing these, start by drawing your initial chair. You always have to start with a chair. Don't worry if you get it right, if you get the right chair in the first place. I just recommend starting with a chair, and then you can go from there. And in this case, with this chair, or actually with any chair you're going to draw for these, remember that the carbonyl on the chiral auxiliary needs to point away from the carbonyl on the aldehyde. And then you're going to fill in your stereocenter. And if your aldehyde is approaching from the opposite side of the bulky group on the auxiliary, then you've got the right chair. If the aldehyde is approaching on the same side as the R group or the bulky group on the chiral auxiliary, then you've got the wrong chair, and all you need to do is to draw the other chair. Okay? That's how you do these. Okay. Now generally with these Evans-Aldol reactions, you're always going to be getting the cis-enolate. So that is one limitation of these reactions, is that it's very challenging to get the trans-enolate product because we can't generally form, or the anti-aldol product, because we generally can't form the trans-enolates. So we're going to get the syn-aldols from the Evans-Aldol reaction. Okay, you can see that was actually the two options that we could really get here, were two different syn products. Now, I want to show you what happens in these reactions when you add a different Lewis acid. Okay, and this is called the Thornton and the Heathcock modification. And that's because those were the names of the two chemists that came up with this. Okay, so the Thornton and the Heathcock modification involves the addition of strong Lewis acids into these reactions. Usually we use titanium. And it's usually titanium 4. Let's see what happens when we do this. So let's take a look at the following example. So in this particular instance, I'm going to use the R configured Evans auxiliary. Last time we used S, so I wanted to show you what it looks like when we use in an enantiomeric form. Okay? What we're going to do is we're going to treat this with LDA to form our enolate, and again we're going to get the Z-type enolate. But then what I'm going to do is I'm going to add in a titanium 4 salt, and we usually use titanium isopropoxide. Okay? And then what I'm going to do is I'm going to throw in benzaldehyde. Now I already know that I'm going to be getting a cis-type enolate, so I already know that I should be expecting a syn-type aldol product. So I'm going to go ahead and draw out both of the possibilities, and then we're going to see how we can predict which one we're going to get. And so there's this possibility where both of the new stereocenters are on wedges, or of course we could get both of these being on hashes as well. So again, the Thornton and Heathcock modification is not switching the diastereoselectivity of the reaction. I'm still getting syn products, but we're going to see that it does still change which syn product we actually get. So the way I want to explain this is by first looking at the standard Zimmermann-Traxler model. Okay? So, if I were going to draw this in the standard way, I would draw it like this. This would be coming up to my aldehyde. And then in the pseudo-axial position, I'm going to put that small group, and then in the pseudo-equatorial, I'll put the big group, the phenyl. And then these are both bound to lithium from the LDA. And then in the back, I've got my chiral auxiliary, and remember, I want the carbonyl of the chiral auxiliary to be facing away from that of the aldehyde. So it's going to look like that. And this would be the correct drawing because the aldehyde is approaching on the face opposite where the bulky isopropyl group is coming from the chiral auxiliary. Okay, and I know that I'm using the R configured chiral auxiliary, and I can confirm that because I've still got R configuration here, so I haven't made any mistakes. Okay. And if we unravel this to get to product, it's going to look something like this. Okay, and if I go ahead and convert that over into a more standard drawing, which again you can do for practice on your own, I'm going to end up getting the double hashed product. Okay. Now notice in this transition state I did not invoke the titanium. So this was the standard Zimmermann-Traxler model. If we were to do this reaction without the titanium 4 salt. So this would be the standard Evans-Aldol reaction. not the Thornton and Heathcock modification. Now, let's take a look at what happens when I add in the titanium. So, here is what happens. I'm going to start by drawing the exact same transition state as a starting point. Except for now, instead of lithium, I'm binding to titanium. Which is a much, much stronger Lewis acid. Now, normally my chiral auxiliary wants to have its dipole canceling out with that of the aldehyde. But if titanium is there, the lone pair on those lone pairs on that oxygen, they're actually attracted to the titanium. So what's going to happen is this bond is going to rotate so that this lone pair can attack the titanium. Let's see what it looks like if that happens. All I'm going to do is redraw my transition state in the same way. Everybody's in the same spot. Although we're about to find out that there's going to be a problem. Okay. So now my chiral auxiliary looks like this. Now the carbonyl of the chiral auxiliary is binding to the titanium. And if I do that, my isopropyl is now pointing towards me. And now the aldehyde is coming on the wrong side. It's way too sterically hindered. So, what that means is everybody needs to flip so that the aldehyde can come in on the right, on the proper side, away from the bulky isopropyl group. And I'm telling you right now, it will take you a couple of tries to find the right chair when you're doing this on your own. Don't be dismayed by that. So when this flips, I'm going to draw my chair like this. And my titanium is going to be over here. And now my isopropyl group is going away, and the aldehyde is now approaching on the correct side. Oh, okay, now I'm avoiding that steric strain. Let's unravel this and see what product we're going to be getting. So, I'm going to go ahead and draw this out. I'm going to get a double bond here. Chiral auxiliary is still the same, in the same spot. Okay, that'll be my product. And if I unravel this, oops, and I want to do this in blue. Gasp, I'm going to get the other product, both on wedges. So what's the significance of this? The significance is, if I do this reaction without the added titanium Lewis acid, I go through a standard Zimmermann-Traxler model. And notice I got the double hashed syn-aldol product. If I add the titanium, it takes that standard Zimmermann-Traxler transition state and it forces the chiral auxiliary to turn around. This whole bond is turning, which means this whole group is coming around to be over here. And it does that because titanium is such a strong Lewis acid and it wants to bind to as many oxygens as it can. That now throws this selectivity all on its head. Now the isopropyl group, or whatever group you might have on your auxiliary, depending on which one you're using, it's now in the incorrect spot. So we have to do a ring flip, and the aldehyde has to come in on the other side. And so I'm going to get this being my favored transition state. This would be the disfavored one, which would give me the double hashed product, okay, which is up there. Okay. But that's disfavored, so we're not going to get that because of that bulky isopropyl group being on the wrong side. The favored transition state involves the flip. Now the blue aldehyde is approaching opposite the side of the isopropyl group. And if I unravel my product, now the selectivity is switched. So the real significance here is I haven't changed the chirality of the chiral auxiliary that I'm using. And yet I've changed which product is now favored. So if I use the auxiliary without titanium, I get the double hash. If I use that same auxiliary with titanium, I get the double wedge product. Normally, if we want to switch selectivity like that, I need to switch the chirality of the chiral auxiliary that I'm using. I would have to use the chiral auxiliary where the isopropyl group's on hash. But that requires making an entirely new substrate, and I have to be able to access or buy that other chiral auxiliary with the opposite configuration, and I might not be able to do that. It might be expensive. And that extra synthesis, those extra steps, is going to add time, it's going to add waste, it's going to lower my yields. But everybody's got a bottle of titanium 4 Lewis acid sitting around their lab, and that gives us a way of easily switching the selectivity in these reactions. So, there you have it. Let's run through very quickly what we talked about here. Before, we saw that if I don't have any chiral auxiliary, my two transition states are enantiomers of each other, they have the same energy, and that leads to a racemic product forming. If I make that chiral, now I'm favoring one of these over the other. I favor this one because that bulky benzyl group on the auxiliary forces the aldehyde to choose one side to come in on, and it won't come in on the other side of the aldehyde because it would be very sterically disfavored. So that basically turns the two transition states from enantiomers of each other into diastereomers of each other. And remember, enantiomers have the identical energy to each other, but diastereomers do not have identical energies. It's the same reason why enantiomers have the same physical properties, right? They have the same melting point, same TLC-RF, same everything. But we know that diastereomers don't have the same properties. So that's what's allowing this to choose one of these products over the other. Now, we learned about the Thornton and the Heathcock modification. That's where you add a titanium 4 Lewis acid that takes the standard Zimmermann-Traxler and it throws everything on its head because of this extra binding interaction right here that wants to occur. And that gives us a way of unlocking the other product. So let me know if there are any questions on this. I will be providing some additional notes so that you can get some more practice with this and see some more examples. All right, thank you.